In the last videos, we saw this new idea of a differential equation, specifically with exponential growth and decay, and when the rate of change is proportional to the y value. That's not always the case. We have all sorts of different differential equations, not just that one example. And so we'll give you a couple of examples here, and we'll see how they look a little bit differently. So for each one of these examples, we are going to find the general solution of the differential equation. The first one doesn't even have a context to it. It's just the rate of change of y with respect to x, dy dx, is directly proportional. Oh, this sounds awful similar to what we had before, but it's directly proportional to x, to the independent variable. That is very different from saying the rate of change of y is directly proportional to y. If we look and see what happens when we solve this differential equation, remember the three steps are still the same though. Separate, integrate, solve. So we're still going to do that. If we separate here, that means moving the x over, the dx to be over with the other x. So that would be dy equals kx dx. And then our next step would be to integrate both sides. And we would get the integral of dy is y. And the integral of kx dx, well, using the power rule to do this antiderivative, kx squared over 2 plus c, which is very, very different from the last example where we had the ln of the absolute value of the y variable. So this is our first solution. Take a look at the next one. The rate at which the height of a Ferris wheel is changing. So this time we're going to think about its variables, because variables actually mean something. So we're talking about the height of the Ferris wheel. I guess I should say the height of the Ferris wheel car, but we'll go with it. And of course, we're talking about as time goes by, so that'll be our other variable. And they're told us the rate at which the height is changing, dh dt, is equal to the cosine of the time that it's been running. dh dt equals cosine of t. And so we will integrate both of those. I'm sorry, I jumped the gun on that. We can't integrate yet. What do I still need to do first? Of course, the first step should usually come first. I need to separate those variables. The dh and dt can't be together. I can't integrate both at the same time, or at least not in the same integral. So I'm going to have to move the dt over. That's not too tricky. So I'll do that over here. dh is equal to the cosine of t times dt. And now we can integrate both sides. And we'll say the integral of dh is h. The integral of the cosine of t is the sine of t plus c. Notice how in these examples, I'm not bothering with C1, C2, or anything like that, because I wasn't going to do anything else after I did the initial integral. The next examples, we might have to do a little bit more. So that's when I'll worry about that. So here we've got another differential equation to solve. The rate of growth of bacteria, and we're measuring the bacteria in square millimeters, is inversely proportional to the square root of its area. Okay, well, that just got complicated. Again, we're going to start by talking about the two variables. We're talking about the amount of bacteria, but that's really the area of the bacteria. And again, we're talking about the rate of growth, so we're still talking about time. Even though the word time doesn't show up here, the fact that it talks about the rate tells me we mean as time goes by. And so we'll translate the sentence they gave us. So the rate of growth, that's dA dt, is inversely proportional. So instead of k times a variable, it'll be k divided by the variable, the square root of its area. dA dt is k divided by the square root of a, which does make sense in some context, I suppose, that the rate at which the area is growing is going to get smaller the bigger A gets. In terms of populations of bacteria, things like this, it does make sense in a scientific way in that there's just fewer resources for the bacteria that's there to grow, so it's a little bit harder for it to continue to grow. That might be why. Anyway, either way, we will go through our steps for solving. Remember, it's separate, integrate, solve. Our A's and our T's need to all be lined up, all the A's together, all the T's together. So we will move the square root of A to be with the dA. We will move the T just to be on the other side. Move the dt to be on the other side. There aren't any T's for it to play with, but that's okay. We don't really need them. We can integrate both sides now. And don't be scared of integrating that square root. Remember, the square root of A is just a to the 1/2. So we can integrate that, a to the 3/2 divided by 3/2, or times 2/3. And the integral of k in respect to t is kt plus c. In this case, however, I do need to do a little bit of work, so I'm going to call this C1, knowing that that might not be the same C that I end up with later. Okay, so we want to get A by itself. Not too complicated here. I'm going to get rid of the 2/3 first by multiplying both sides by 3/2. And this is why it's helpful to have that C1, because multiplying the kt by 3/2, I'm going to need the 3/2 there. Excuse me. But multiplying the 3/2 by some constant is just going to give me some other constant. So what I'll have on this side is the a to the 3/2 is equal to 3/2 3/2 kt plus, instead of writing 3/2 C1, I'm just going to call it C2. Still just some constant. And then to get my A all by itself, a to the 3/2, I'm going to raise everything to the 2/3 power on both sides. And so we'll have A equals 3/2 kt plus C to the 2/3. I could still call it C2 if I want, but I'm done now. I'm not going to do anything more, so I don't really need to be specific about how many C's I've used. That's just the C I ended up with. We'll do one more. I think this one's a little bit quicker. The rate of change of x in respect to y, dx dy, notice how that's a little bit backwards from what's used to, varies jointly as x and y. That's something from your Algebra 2 year. It just means that it's the same thing as varying proportionally, just with two different variables at the same time. And so when we separate here, we'll have a little bit more, we have to worry about both variables. So I'm going to need to bring my x over to the same side as my dx. I'm going to bring my dy over to the same side as the y. It doesn't matter where the ky is. I'll just leave where the k is. I'll just leave it in the numerator. And so then when we integrate both sides, and so this one is going to end up looking similar to what we had before, because we again have the ln of the absolute value of x, so we're going to need e to sort of deal with that. But what's going to be different, the only thing that's going to be different is because this y was here all along, it means that our solution is going to have a slightly more complicated y squared in it, but But other than that, it's really the same thing as before, where we can exponentiate both sides to deal with that ln. And I know what's going to happen now. E to the ky squared over 2 plus c1. I'm going to write that as e to the ky squared over 2 times e to the c1. And that e to the c1 is just some constant. And then really the absolute value of x could be a plus or minus. But since c is some unknown constant, really I guess I should have called this c2. Since c is some unknown constant, I don't really need to worry about the plus minus. So I'm going to get rid of it in just a second anyway. And so that would be my final solution.